third year advanced ICT student at Western Sydney University, and I'm joined by...
Hi, my name is Andrew Smith. I'm a third year Bachelor of Computer Science student.
Let's get into it. So today we're going to be covering why we need race strategy and some of the factors that come into play during the Bridgestone World Solar Challenge. Then we're going to start talking about some of the existing approaches to race strategy. And finally, we're going to talk about how we've had to change our approach for the upcoming Aussie Solar Challenge. So just some context on the event itself. The Bridgestone World Solar Challenge, or BWSC for short, is a 3,022 kilometre challenge from Darwin at the top of Australia, right down to Adelaide at the bottom. It runs every 2 years, but due to the COVID-19 pandemic, it was cancelled for 2021. The challenge takes place over a week, and teams are only allowed to race between 8 AM and 5 PM. There are 9 set control stops along the route, which you can see on this map to the right of the screen, where the team must stop for 30 minutes and aren't allowed to touch the car during that period. We start the challenge with a fully charged battery pack, and we cannot use external sources of power along the route, except for sun, of course. That means no plugging in along the way to get us to Adelaide. Our goal in the BWSC is to be the first across the finish line in Adelaide. Let's introduce our car for the BWSC. This is Unlimited 3.0, or TED3 for short. This was a car that we designed and manufactured for the 2019 BWSC, and the team worked to optimize every aspect of the car for efficiency. This ranges from the aerodynamic design of the car, and almost completely carbon fiber construction, specifically chosen low rolling resistant tires, and weight savings taken wherever possible. This led TED3 to be the lightest solar car to ever compete in the BWSC, weighing in at only 116.8 kilos. So we can see that we're bringing a very efficient and well-designed car to the BWSC. And as mentioned, this car has a battery. Regulations allow us up to 20 kilos of batteries, depending on the chemistry. Lithium ion and lithium polymer battery chemistries are common, and it's sort of up to the team's decision. So let's see how far we can get with that 20 kilo battery. Because TED3 is so efficient, we can travel around 400 kilometers on a single charge. And for context, a modern consumer electric vehicle only gets around 35 kilometers with that same amount of energy. So we can conclude that TED3 is a very efficient car, but efficiency on its own isn't enough for the BWSC. Alone is only going to get us part of the way. So we're going to need something more than a 20 kilo battery and an efficient car to complete the BWSC. So the energy in our battery won't be enough for the BWSC, but we are a solar team after all. So we must rely on solar power to get us the rest of the way. Over the duration of the challenge, we only expect to get around 13% of the energy from our battery, with the sun providing the other 87%. So over the duration of the challenge, we would expect to accumulate a certain amount of solar power. And then when we combine that to the energy that's in the battery at the beginning of the challenge, we get this whole circle, which is all the energy we'll have available to us on the challenge. So if our goal is to cross the finish line of the BWSC first, we'll need to go as fast as possible. This means making the most effective use of all this energy, or the entire circle you see on the screen. However, solar power is not quite that simple. We can't treat the energy we get from the sun like we do the energy in the battery, because it's not all available to us in one go. Rather, it's accumulated through the challenge. Now, solar power varies predictably throughout the day as the position of the sun changes, most solar power being available at solar noon. So on this plot, the y-axis represents power, or irradiance from the sun measured in watts per meter squared, but for simplicity, we'll just talk about it as power measured in watts. Along the x-axis, we had time, in this case spanning a day. Therefore, the height of this curve is the power we get from the sun at any given point, and then the area under the curve is the energy we'll get from the sun over that day, because energy equals power times time. Just a quick note on what power is and what energy is. Let's take our car, and let's say we're traveling at 100 kilometers per hour. And that's making us consume 1000 watts or 1 kilowatt. And we'll represent that by this white line. If we then ask the question, how much does our battery drain? Well, we can't answer that without a time component. So if we're traveling 100 kilometers an hour for 1 hour, then we're consuming 1 kilowatt hour of energy. And if our battery pack is 5 kilowatt hours, well, then that would drain 1/5 of our battery. So let's pick a point along this line. At any given point, we'll have a certain amount of power coming in through our solar array, represented by this yellow rectangle. Then if we combine that with the power we can draw from the battery at any given point, we therefore get the total power we can use at any given point. The blue bit is the battery, yellow is the solar power. Now, of course, we can only draw energy from the battery if it has any charge remaining. So, since we are an electric car, the motor that drives the car is the main power consuming component of the car. And the power it consumes is largely dependent on the speed that we're traveling. If we're using the same amount of power as the solar panels are providing, then we're neither charging nor discharging the battery, as you can see in this scenario. If we're using less than the solar panels, well, then we're charging the batteries, as this extra solar power can go straight into the battery. However, if our battery is full, then this energy just goes to waste. So therefore, during the challenge, we don't want to have a full battery for very long, because if you recall, we want to use all the energy available to us. We don't want to be discarding any. Now, if we're using more energy than the sun is providing, well, then we've got to drain the battery. But this isn't necessarily a bad thing, as the battery provides the flexibility to choose a speed not entirely dependent on solar power. However, if the battery is completely dead, well, then we can only go as fast as solar power will allow, which severely limits our options. So we've established that we rely heavily on the sun and that solar power varies throughout the day in a predictable way. However, the sun isn't always reliable. For example, if the sun's obscured by clouds, that can greatly reduce the amount of energy we get from the sun. And if we're going to get less energy from the sun, then we're going to need a different strategy. So if we've calculated a speed that we should go, and then we're going to get less energy than we expected, well, then the ideal speed would be slower than we planned for. Therefore, we need to recalculate our strategy, and that can get quite complicated. But that's why we've partnered with companies such as Cellcast and WeatherZone to provide best-in-class irradiance forecasting. So we can know ahead of time how our solar power is going to vary based on external influences, so we can plan ahead. However, a forecast is never 100% accurate, so we still do need an adaptable strategy system. So let's just quickly recap. Our goal is win the BWSC. Our strategy is to go as fast as we can. Therefore, we need to use all the energy available to us, and this means managing our power consumption during the challenge. And power consumption is correlated with speed. Therefore, the goal of race strategy is find the optimal speed at any given point to achieve this goal. Let's look at a real-world example, the 2017 Bridgestone World Solar Challenge. 2017 was a year with uncharacteristic and severe weather, including storms and rain, which are atypical to face on the BWSC. Faced with dark storm clouds ahead, the 2017 team was presented with three main options. First option is, do we go the same speed, knowing that we're going to get less power from the sun, therefore our battery is going to drain more than it otherwise would have. The second option is to slow down to account for that loss in power. It may take a bit longer, but your strategic position in terms of battery state of charge won't change. And then the third option is to speed up to try and get ahead of the clouds. So while you use more energy going faster, you hope that by spending less time under the clouds, you can get more overall solar power. And while it may sound counterintuitive, option 3 was shown to be the best option. Because as discussed earlier, solar power is the source of the majority of the energy on the challenge. Therefore, maximizing that is more beneficial than preserving battery power in this scenario. So all the teams that chose option 3 had an advantage over the teams that chose the other options. So seeing why we need race strategy, I'll now hand over to Andrew, who will talk about how we can make these strategy decisions.
All right. While this plan may sound fairly simple in that we need to go as fast as possible from Darwin to Adelaide, it doesn't necessarily mean that we can sprint down the Stuart Highway at 130 kilometers an hour. We need to use the data available to us to choose when we can go fast and when we can go slower. To make these decisions, we need to be able to simulate our solar car. We can look at how our decisions play out in future in order to make the best decision now. With sufficient work, Our system is able to adapt to changes in conditions such as a sudden change in weather or potentially anything else. However, it comes at a cost. The number of possible choices that can be made in the Bridgestone World Solar Challenge is potentially more than there are atoms in the universe, depending on how you calculate it. As a result, we need strong and capable compute power, a benefit of working with Amazon Web Services. So we've seen all the factors that we need to take into account. We then piece them together to form our system. Our current car state, consisting of battery state of charge, solar power in, and power used, in conjunction with the weather information we get from Solcast and Weather Zone. These form inputs into our strategy system powered by AWS. This system will give us the target speed we can travel for optimal performance. One of the unique elements of the strategy subteam compared to other technical subteams that make up the solar car teams is that we're not necessarily bound by the regulations in what we do. As a result, you can find different examples where different teams have approached the Bridgestone World Solar Challenge in their own ways to try and find the most optimal solution in completing the 3,022 kilometers. A prime example of this is some of the work done by Peter Putney and the University of South Australia for the Aurora Solar Cup team, titled Optimal Energy Management for Solar Powered Cars. This work details the entire solar car problem and how to work to calculate an optimal strategy, which helped bring the team to victory in the 1999 World Solar Challenge. In previous years, other teams across the world have published some of the details of elements of their strategy systems, such as the University of Michigan publishing their work in collaboration with IBM in creating a solar forecasting system along with a sky camera, and the Vattenfall solar team using genetic algorithms. While these systems help achieve the goal of traveling from Darwin to Adelaide as fast as possible, none of this is actually required to be done as per the regulations beyond meeting a minimum speed requirement of 60 kilometers an hour. Here's an example of a solar car. Given the parameters on screen and the expected values for battery power and the power intake during the Bridgestone World Solar Challenge, we can calculate the expected average speed during the entire challenge. While it's not completely accurate, as it doesn't account for the incline and decline during the challenge, and it can provide a general idea of expected performance that can be used to evaluate the design or provide an immediate strategy option. However, there's more to it than that. The Bridgestone World Solar Challenge takes place over 8 hours per day for 7 days, and the daily solar readings can be represented as such. Bringing back the energy graph from before, we can pick a few points along the curve to decide our energy input at any particular time. We can represent these as a number, in which this case is the number of kilowatts or thousands of watts the car receives in an hour. By arranging these numbers into a 7x8 grid where each row is a day and each column is an hour, we can create a basic representation of the Bridgestone World Solar Challenge. Here in this example, a constant amount of solar readings is received over each hour of each day, except for day 3 where it decreases during the day, and day 4 where no solar power is available whatsoever. This exact scenario is extremely unlikely to occur during real life, as the solar radiance tends to follow a curve during the day where it tapers off at the start and end of each day. Having a full day of 0 solar radiation is also not realistic, but serves to demonstrate how radiance can vary with differing conditions. By knowing the parameters of our car, we can model how much power the car will use when moving and use that to construct a model. One approach is that we try and keep the car neutral and the power into the car is equal to the power used, as shown by the bottom number in each cell. However, as shown, that comes with a cost, in that in times of low to no sunlight, the car significantly slows down and is at a stop when there's absolutely no sunlight, as no power is running into the car. The advantage for us is that the car has a battery. So from this, we can calculate the speed in which the car drives as fast as possible without running out of charge before the finish. By driving at a constant speed, we can quickly calculate a strategy in which the solar car completes the Bridgestone World Solar Challenge without running out of charge while going as fast as possible. The previous approach, however, only looks to calculate a singular speed to complete the entire challenge. While it works, there's many other approaches that can be taken. This is where you start to see a large amount of complexity, while in the previous model, there's less than 50,000 possibilities. So calculating them all is pretty straightforward. It can be adjusted where there be potentially billions of possibilities. By analyzing a greater number of possibilities, we can hope to arrive at a better strategy than simply picking a single speed. Imagine that if each of these given circles is a state that we find ourselves in, each circle represents being at a certain point along the route with a certain battery state of charge, certain weather conditions, and so on. Each of these orange circles is reached based on the decisions we make represented by the black lines. So if we expand the decisions we make to include different speeds at different points along the route, we massively increase the number of orange circles we need to consider. Calculating these possibilities requires a large amount of computing power. Oh, we lost the light. Calculating these possibilities requires a large amount of computing power. Having a large amount of computing power works to increase effectiveness and broaden our horizons on what's possible. Thankfully, working with Amazon Web Services, we can transform ideas of imagine if we could to how do we. So we've seen how we can build a basic strategy system for the Bridgestone World Solar Challenge, but let's look at how a track-based event changes things. Following the cancellation of the 2021 Bridgestone World Solar Challenge, the Aussie Solar Challenge was created. While it was also postponed due to the recent COVID-19 lockdown in Sydney, it presented a new challenge for us. The Bridgestone World Solar Challenge is a road-based challenge, whereas the Aussie Solar Challenge is track-based. Here, we have to account for frequent acceleration and deceleration in cornering speeds, unlike the Bridgestone World Solar Challenge, where this is largely not a concern because we're mostly at a consistent speed along the motorway. As a result, we've had to completely rethink our strategy system from the ground up. Thankfully, this is an area that is being worked on by other people in the area of Formula, SAE, robo-race, and much more. With the known parameters of our car, we can simulate a single lap around a track. However, that's not quite enough. If you piece many of these simulations together at varying speeds to the level of possibly hundreds of laps, you can create a simulation of the Aussie Solar Challenge to inform strategy decisions. With this, we're able to face this new challenge with confidence. Thanks for listening to us today. There's a QR code and a link to connect to contact details that we'll reference in this presentation. The rest of the session will be for questions and answers. Thank you very much.
Thank you.
Cool. Well, thanks, Jono and Andrew for that. That was great. Very informative. I guess we'll go over to the Q&A session now. One question we've got in the chat is, are commercial solar panels used in the vehicle?
That's a really good question. For 2019 on TED 3, we used gallium arsenide chemistry, which is commonly used on things like space telescopes and satellites. So they're not really commercial grade. However, the 2023 regulations have actually prohibited that type of solar panel, largely based on the grounds of it not being a very sustainable thing to produce. Other solar cars tend to use silicon-based solar cells, and those are closer to what you'd find on a house, for example. However, the encapsulation type is quite different, and there's many other factors at play that make it a bit different to your typical commercial installation.
Yeah, great. That's good points to consider when choosing your solar panels. Another question that we've had is, do you ever get nervous before a race? And following that, how do you manage team morale in the face of challenges like the bad weather in 2017?
I'll let Andrew answer that one.
Well, I guess it's always something to be somewhat nervous to looking towards of starting something, because you've just built and designed a car that has to travel over 3,000 kilometers in some of the harshest conditions in the country, or potentially even the world. So getting that ready to go can be quite nerve-wracking. And then how do you manage team morale in the face of challenges like the bad weather of 2017? I personally wasn't there in 2017, so I can't really speak to that, unfortunately.
Yeah, neither was I. But I guess we can use the example of 2021 with the race being cancelled and then a replacement race also being cancelled, or postponed, I should say. And yeah, team morale is a hard thing to manage, but you've just got to push through it. And we fortunately have quite a close-knit team, and we've managed to overcome the 2021 challenges and come up with new things to keep us busy, such as this virtual expo.
Yeah, that's great. Another question, how long is the challenge?
Yeah, so as mentioned, it's a 3,022 kilometer challenge. I'm assuming this is in regards to the Bridgestone World Solar Challenge.
Might be good to touch on both BWSC and...
So yeah, it takes place over 7 days, but I think most teams finish a fair bit quicker than that, typically in closer to 5 days. As for the Aussie Solar Challenge, that's over 2 days around the track, and the track is 2.2 kilometers long. Yep.
Yeah, that's great. I'm not sure how much you can expand on this, but maybe give a quick summary of, we've got a question of how does your telemetry system work?
Yeah, so none of us work directly on the telemetry system, but it worked quite similarly to most telemetry systems in the sense that the components of the car are hooked up to a CAN bus, and then that gets wirelessly sent out to the chase vehicle, which records all of that telemetry data. It uses the MQTT protocol. Outside of that, I can't really give you too much more detail because I'm not too sure on the specifics.
Yeah, that's all right. Another question that we've got in is, what role does AWS play for the solar car team?
Yep. So it sounds fairly counterintuitive working with a cloud computing giant to race in the middle of nowhere for 3,000 kilometers, but thankfully there's advancements in edge computing and stuff, so we can bring that large amount of like cloud computing power that they bring to locally in order to sort of take advantage of what we've built online. Plus, we're able to use it to develop and test internal systems and even push externally in some cases. We've built like a virtual racing simulator, well, leaderboard during lockdown as a bit of a, I guess, a task to learn AWS ourselves.
And just fun for the team.
Yeah. We've tested our brand new website, which is now live. You may or may not have seen it already. And that incorporates elements of AWS and much more. And we're working to sort of advance and push our strategy systems as far as we possibly can using cutting edge technologies.
Yeah, that's great. That's awesome. We've got another question here, which is, about fundraising. How many team members are focused on fundraising in the team, and what's, sort of a rough number? What's your annual budget?
I think someone like Brad might actually be better to answer.
Yeah, let's pass that one on to our team manager, Brad. If you want to give some words on that.
Yeah, absolutely. So our team, is tasked with raising funds to secure budget to run the project. And it really depends on the race cycle that we're running as to what the budget is. For example, a year like 2019 saw us run with a slightly higher budget than we normally would. So to give you an idea of the cost of those gallium arsenide cells Jono and Andrew spoke about earlier, those cells alone were about $400,000. So not cheap technology. And in fact, as far as I'm aware, that's one of the reasons they actually were banned in the 2023 race, to even out the playing field, because obviously not everyone has access to a budget like that. But generally, we run anywhere between $500,000 and $800,000. Yeah, hopefully that answers the question.
Another question that we've got in is, what degree are you pursuing, and what contributions have you made to the challenge? I'm guessing so far towards the 2023 Bridgestone Challenge.
Yes, so at Western Sydney Uni, I'm studying advanced ICT, so information and communications technology, and also a Bachelor of Applied Data Science. And
Yep, so I'm studying a Bachelor of Computer Science Advanced.
And that helps us greatly on the strategy team, because as you can imagine, computing possibilities on the challenge requires programming. So we've taught program through university. So we tend to use Python as our preferred language and environment to work in. So we just, that's how our degrees mainly helped us. And obviously having a bit of experience with data analytics helps when we're getting telemetry data and such.
Yeah, to follow on that, would you say that using you've been able to use what you've learned in the classroom and apply it physically?
100%.
Yeah.
And this has been one of the best opportunities at uni to do this. And really anyone in any field of study can play a role in this team, because it's very disciplinary.
Yeah, that's great to hear. Another question here, we might pass this on to Divyam, our systems and interface lead, but the question is, how progressed were the plans for the race at Wakefield Park, and what vehicle characteristics will be beneficial for the Wakefield event versus the Bridgestone?
That's a great question. So the plans for the race at Wakefield were quite advanced. The committee was set up. The regulations were more dependent on following Bridgestone regulations and car that had cars that have previously passed the Bridgestone regulations. But the characteristics that are beneficial, there's quite a few differences. Being a shorter race, obviously solar generation plays less of a factor compared to your battery capacity. That's obviously a big thing. You're also accelerating and decelerating a lot more. So motor efficiency plays a much bigger factor, and your cycle efficiency for your battery also plays a much bigger factor than the Bridgestone World Solar Challenge. Rolling resistance is less important as well, because we will generally find we're traveling at much lower speeds compared to what we are in the Bridgestone World Solar Challenge. But I think the most important thing, and this was quite evident when the team competed in the American Solar Challenge, where they had to do Formula GP, which was a short endurance race before the main event, was just how many of the highly efficient cars kept breaking down, and they just couldn't finish the challenge. And the cars that won weren't the prettiest or the most advanced or the most efficient cars. They were the most durable ones. They were built in a way that they wouldn't break by going around corners. So most solar cars are really designed for straight line, and what we're focusing on is getting a car that's going to be reliable over 2 days of track driving, which is way different to just driving in a straight line. And I think not breaking down will go a long way in winning the Aussie Solar Challenge.
Yeah, I agree with that. And another question, we'll go back to Jono and Andrew for this one. A great question. How do you simulate race conditions, and why do you need such a large amount of computing power from AWS?
So basically you rely very heavily on your HSC physics class. So you just program in the environment that the car exists in and the forces acting on the car, and then how that translates to power consumption. And you generally keep your physics model fairly simple, at least in the case of the Aussie Solar Challenge, because we're not F1, we're not sending the car around the track at the fastest possible speed, we're aiming for efficiency. It's not vital that our handling characteristics are 100% accurate or anything like that. So you basically take into account how much force the tires can provide, how quickly the motor can accelerate and decelerate the car, how much the car weighs, elevation of the track and such. And then from that, you can calculate your power consumption. And in terms of why do we need AWS for this? Because the race simulator that we've built can calculate a lap around Wakefield in under a second. So it seems like we might not need AWS, but in reality, you can get the better strategy by doing that lap over and over and over again in slightly different scenarios and in different combinations, and then you can figure out what the best strategy is from that.
Yeah, that's great. A lot to consider there. The second last question that's come in is, has the virtual race simulator led to any changes in your strategies?
Not directly as of yet, but it has been a good practice run for when we can do track testing, how we can analyze that telemetry data from around a track, how we can evaluate drivers, and then how we can sort of manage our real world performance based on our expected simulated performance.
Yeah, nice. Another question, what are the main challenges for the driver? Cockpit temps, endurance racing, what else?
Yep, I think those are the main two. You got to sit in a little carbon fiber box that can get as hot as 60 degrees Celsius for extended periods of time and pay attention to the road. So that's quite a challenge in itself. And then you need to manage other cars on the road. The Bridgestone World Solar Challenge takes place on open roads, so you have to manage traffic, have to do overtaking of road trains and such. And for the Aussie Solar Challenge, you're going to be on the track with several other solar cars, and they're all going to be doing different speeds. So you're going to need to manage how you take corners, depending if there's another car in your way. So there's a lot of work that the driver needs to do, and we've got to try and prepare them as best we can for that.
One last question that we've sort of touched on a little bit already, but what challenges did the team face, and how did you resolve it?
Yeah, I'll give that one a shot. So I guess first challenge was, in most recent memory, is changing to track-based racing. Well, at first it wasn't quite a priority. After a bit of discussion, we sort of it was sort of, I guess, became aware to us that, hang on, we're not at least prepared in a strategy sense to approach an endurance event around the track compared to an endurance event in what to us is essentially represented as a straight line from Darwin to Adelaide. So then that led to a lot of research days, just sort of working away at our problems to try and see, all right, how does this look? Does this work? Lots of standing around a whiteboard and discussing and drawing up plans and everything.
And then that moved to Zoom during the COVID lockdowns.
Yeah.
Andrew and I have been on Zoom basically all day working out problems.
Yeah.
Yeah, awesome. Well, thanks guys for that. That was really awesome. Really great to, you know, hear all your thoughts and you know, how you go about your work here at Solar. But now I'm gonna hand it over to Brad so he can finish up the session for us. But yeah, thank you.
One more question in the chat, which looks quite interesting.
Oh yeah, we do. Thanks, Stephen, for that one. The question is, how will decisions be made if human intuition and computer modeling are giving opposing answers to a problem? What's more important, driver feedback or model feedback?
Well, driver feedback, if it's in the sense of safety, obviously takes #1 priority. If we're telling the driver to do something and the driver doesn't feel comfortable with that, well then of course that takes priority over whatever the computer's saying. And the same goes with sort of battery management, like you can't drain your batteries too much. So obviously if the computer is telling you to go faster, but that wouldn't be safe to do so, you obviously override it there. But to be honest, it's a mix of the two. We try and make our computer models as best as possible. And we also want to build the tools in addition to the main system to supplement that. So if something changes and there is a disparity between like human intuition and computer intuition, we have the tools to manually assess the situation better rather than just purely automating everything. So I hope that answers the question.
Awesome. Well, yeah, thanks, Cheryl and Andrew. I suppose I'll wrap it up now just by saying, you know, thanks to the team and thanks to everyone, especially for joining the session. You know, I hope you learned a lot about race strategy and how that all works. And, you know, if you'd like to get involved with the team or to partner with us to help us win that 2023 World Solar Challenge, please let us know. We'll post some stuff leading on from this event, you know, inclusive of hopefully this session itself, so you can rewatch and distribute it to family and friends. But yeah, thank you very much, and hopefully we'll see you at some of the following sessions.